I'm guessing no, that's not showing the presenter view, is it?
No, so we're seeing the PowerPoint, the editing view.
Right. But I probably need to swap. Is that better? I guess
Yes,
so,
yep,
right?
perfect. We see
Okay.
your slides now.
Great, fantastic. Okay, I guess hi everyone. My name's Billy. I first gave a talk last year at AUCAOS when we were out at the Blue Mountains. So I'll be following up with some more work that we've done in the same area. So effectively, what we work on over at UNSW in the Electron Spin Resonance Lab under the supervision of Professor Dane McCamey, we look at spins in organic semiconductors and we think about how the interactions can lead to interesting device applications that might not be so obvious on first glance. So I guess I'll start off with an introduction of what makes spin interesting in organics, and that is that there's weak spin orbit coupling. So that weak spin orbit coupling generally leads to long lifetimes and coherence lengths of these spins. So that becomes interesting in the first class of Spintronics devices, I guess, where you can inject, manipulate, and transport spin through the organic layers between two ferromagnetic electrodes, for example. And the first spin valve, for example, was made all the way back in 2004. But since that time, I guess the focus has shifted a little bit more to spin logic devices. So it goes to show that spins in organics has a lot of potential moving forward. But even though the weak spin orbit coupling exists, there is still a dominant hyperfine coupling in these materials. And so in order to get the most out of working with organics, we need to really understand how the hyperfine interaction affects our spins in these devices. And particularly what I look at is optoelectronic devices, most of the time with OLEDs, but that also includes OPVs. And what we do is we look at how the hyperfine interaction leads to certain magnetic field effects, which we can then use to manipulate the devices so that we can optimize efficiency, for example, but it goes much further beyond that. And I'll come to that shortly. But I guess the important distinction between these two classes of Spintronics devices is that the top one, which is organic Spintronics, deals with manipulating coherently spins through these layers, whereas the intrinsic spin effects, which is what I deal with, is really all about manipulating spin selection rules with external magnetic fields. So I guess this leads on to why we've done this work in characterizing basically the hyperfine interaction in these organic materials. And that is, if we want to miniaturize and integrate these quantum technologies, then we need to understand what the microscopic variation of this effect is. And so to explain what I'm talking about, we'll have a look at something called an OLED magnetometer. So it turns out that you can use an OLED to detect an external magnetic field. So if we look, hopefully my mouse is working. So if we look at this first figure at the top, what you can see is that there's a micro strip line, which is pretty much sitting underneath an OLED. And it turns out that you can generate a magnetic field, an oscillating magnetic field. So it's pretty much a microwave field using that microstrip line. And if there's an additional external field somewhere on that OLED, turns out that you can detect that. And that's what happens when you sweep through the frequency of this strip line. And so then these are used as robust absolute magnetometers, right? So they don't need to be, what's the word? Previously, so there's no calibration, sorry. There's no calibration required to do this. It's an absolute measure of the external field. So that's very, very important. And especially they're very easy and cheap to make. So these offer a lot of potential. And this was back in 2012. And so if we look more recently at 2017, we see that we're going for miniaturization because then it's much easier to integrate these quantum technologies into a whole array of other devices. And so we start off from 6 millimeters squared going down to 57 microns squared. And you can see that the sensitivity is still there. It still works as intended. But there are several important questions which need to be answered if we want to go down this route. And so, for example, we might ask, how does the line width change with the device sample size area? do the microscopic variations in these properties affect the sensitivity or the reliability of these measurements? And if there is some spatial correlation of these spin properties, which in our case is a hyperfine interaction, over what length scale do they remain uniform? And the reason why you might want to know that is if you fabricate a device that's within this length scale, then you can be fairly confident that the response from this device would be fairly constant. Whereas if you're above this characteristic length scale, then there's going to be fluctuations in your device which become more important the smaller you go. So now I'll give a quick introduction into the excited states, which occur in these organic materials. Let me just have a look. 5 minutes, great. Okay, so if we start off, we see our free charge carriers. By the way, this is a much more simple explanation than Daniel just gave, which was fantastic, but we're just going to stick to a simple hopping transport mechanism where the charges are localized to their sites. And so what happens is when they hop to within something called the Onsager radius, that means that they start to feel each other's Coulombic attraction. And so we say that they form an intermediate state, and that's known as a polaron pair state. And depending on the spin of each of these guys, they can either form a triplet or a singlet state. And here we're talking about the total spin permutation symmetry. So from here, there are two pathways that they can take. The first is that one charge can hop away from the other charge and we can get dissociation. But what we're more interested in is the second pathway, which is where they hop onto the same site and they form a tightly bound exciton. And depending on the spin state, whether it's a singlet or a triplet, it will undergo fluorescence or phosphorescence. So for OLED applications, we can measure the fluorescence quite easily. It's just the brightness of the device. And so that tells us that the changes in brightness are sensitive to modulations in the singlet and triplet concentrations of these polaron pairs. And I guess that's quite important because this is where the magnetic field effects take place in this intermediate regime. The reason why they can't take place in the excitonic regime is due to the large singlet triplet energy splitting, which comes from overlap with the wave functions and the exchange coupling. So moving forward, let's have a look at what this hyperfine interaction is. So if we look at one charge carrier, say the hole, we see that it's delocalized over some part of the molecule. And this delocalization of the wave function encompasses several nuclear spins. So it turns out that each of these nuclear spins interact with the spin of the charge carrier, and the net, if we take a vector sum of these nuclear hyperfine fields, I guess, then you can approximate that to a single field known as the overhauser field. Now, the overhauser field, pictured as the green arrow, can be seen, I guess, just I've put it on top of that charge carrier. And then what we can do is think about the spin of the charge carrier precessing about this overhauser field, which encompasses all hyperfine interactions in that wave function. Now, what happens is hopping occurs, of course. And so each time our electron, in this case, hops to a new site, it's going to integrate over different types of nuclear spins. And so we're going to get a different overhauser field with each hop. When we make it to the site of the neighboring molecule between the two charge carriers, we call this the final intermediate states between the hole and the electron. And so what will happen is this electron will precess with some frequency, some Lamore frequency about that overhauser field, and the hole will do the same about its own overhauser field. The fact that these overhauser fields are different means that we open up channels to mix between the singlet and triplet manifolds. And so rather than having just a static like singlet polaron pair or triplet polaron pair, we can actually oscillate between the two manifolds due to this spin mixing. So effectively what I'm trying to say is that the hyperfine interaction opens up some singlet triplet interconversion pathway. And so that's why understanding how the hyperfine field varies within the device is fairly important, especially if all your results or the application of the device depends upon the concentration of singlets and triplets in the device. Anyhow, so if we look at what would happen at the next step when it forms a tightly bound exciton, we see that actually the spin symmetry that it was at in site 3 is locked in. And the reason why this is the case is if we look at the rate of precession, we see that it takes about 7 nanoseconds for a typical precession in a field of about 5 millitesla. However, the recombination rate when this hop occurs and I guess the exciton, if it's a singlet, the exciton emits, is quite fast compared to this precession rate. So for all intents and purposes, these spin permutations are locked in at the point at which it makes the hop. So that's how we can get into the point where it's an intermediate state, and we can do some manipulations, which I'll show you in a second. And then once the exciton forms, those spin permutation symmetries are locked in. Now, if we look at a typical field effects, which occur here, then what we see are two things going on. So in order to simplify this briefly, I'll ask you to just focus on the red line. So what's happening with this red line is we have an external magnetic field being applied to our OLED, and that external field is represented by B0. As we apply this field, we see that there's some increase in the current, and we call this magnetoconductance. And so when we follow this line and we see this width, we find out that actually the B half, which is the half width at half maximum of this curve, scales with the hyperfine interaction. How do we know that? Well, we know that because if we take a material, which is hydrogenated, so just proton spins, and then we deuterate that material and perform the same measurement, what we see is that this half width becomes narrower. And the reason why this occurs is because actually the hyperfine interaction strength represented by AHF for hydrogenated and deuterated, or hydrogens and deuterons, I guess, is different, differs by a factor of about 6.5. And we see that this width scales by approximately that amount. So this is pretty surefire evidence that the hyperfine interaction can be measured by measuring the width of this B half to some scaling factor. And so if we want to understand why this curve has the shape that it does, ignoring the ultra small effects for now, then we just look at what's happening with the spin permutation symmetry, or the spin mixing that I described in the last slide. And so what we see is when the external field down here is of the order of the Overhauser field, so represented by that green arrow, then we see that actually these guys are precessing at around fairly random axes and with different precession rates. So there what we say is that strong spin mixing is occurring. And so then we see a sharp rise as we move the field when this guy's in the regime of the hyperfine field. However, as we go to much larger field strengths, we see it starts to saturate. Effectively, what's happening is we get some effective field where we have the external field plus the Overhauser field. And this effective field now minimizes the difference between the angle of precession, but also the rate of precession between the electron and the hole within the polaron pair. And because this difference in precession is minimized, effectively we get an ever decreasing change or suppression in the spin mixing. And the reason why I say that is when these guys are precessing together, effectively we don't have this oscillation between the singlet and triplet manifold anymore. So we say that we're suppressing spin mixing, or that we have weak spin mixing. Now, moving over to the second, I guess, type of measurement that we can do, known as magnetic resonance measurements, what we can actually do is induce spin mixing. So unlike MEL, which suppresses it at larger fields, magnetic resonance acts to induce it artificially. And so I guess effectively all we need to know is that this exhibits the same behavior in the hydrogenated and the deuterated material, where the line width narrows. And so this indicates that both of these effects are taking place due to the strength or the interaction with the hyperfine fields. So anyhow, to recap why I've introduced this slide, it's basically to show that these effects can be used to probe the hyperfine fields, right? So we start off with our measurement, and we start off with electrically detected magnetic resonance. So that was that second form of measurement I just discussed. We have our OLED over here pictured under a microscope. That's the structure. So it's a prototypical OLED super yellow PPV. And then we apply our external field, B0, and then we have our secondary B1 field from a resonator, which we fabricated. And so what we want to do is induce spin mixing and measure these widths to find what the hyperfine field is. So if we look at what a typical experiment looks like when we do this experiment, what we're seeing is that we apply a 10 microsecond pulse of the B1 field. And as we apply this pulse across where there's some B0 of 815 Gauss, we hit resonance and we see a quenching in the current. So if we look over here, we're measuring the current in the device, see some prompt quenching followed by some delayed enhancement of the current. And so if we do this for several magnetic field values, what you're going to get is some mapping that looks like this, where we have our magnetic field on the y-axis and the time after pulse on the x. And so if we take a horizontal slice, we're going to get what we just saw. But actually what we're interested in is measuring the broadening due to the hyperfine field. So what we're going to go and do is take a vertical slice of this guy, and then we have some broadening now, and that broadening is hyperfine induced. So this is pretty much going back to a few slides back where I explained this effect. This is what it looks like, I guess, on a molecular scale. And the reason why I say on a molecular scale is each of these contributions is coming, sorry, this distribution reflects the distribution of hyperfine fields, as each contribution can be thought of as the hyperfine field plus the external magnetic field together, making some effective field. So you can tell that out here we hit resonance early, and that's because the hyperfine field is lining up with our externally applied fields, and so on and so forth. Anyhow, so we've done both electrical and optical detection to show that these processes arise from the same origin, and we can decompose. So if we take one of these signals, the EDMR, we can decompose this into two normal distributions. So the line fit itself is a double Gaussian, and each constituent Gaussian arises from targeting the hole or the electron within all spin pairs in the organic material. And so if we go back to this idea of the polar pair, what we have is a hole sitting on this side, an electron on that side, and these guys form a pair together. And so with EDMR, we're able to hit resonance with the hole and the electron separately. And that's how we can decompose these two normal distributions. But actually, it turns out that this isn't a good method for trying to detect spatial resolution of the hyperfine fields. And the reason behind that is ODMR is incredibly tricky to get. So the induced change in due to a magnetic resonance pulse is about 10 to the -4. And so in order to get a high enough signal noise ratio at small enough scales is really, really difficult. So instead, what we're going to do is we're going to go down a secondary route, which is MEL. So now MEL was that first effect I introduced earlier, where I talked about spin mixing being suppressed as you apply this external magnetic field. And what we do is we've built up a setup in order to do this. So we've effectively just incorporated microscopy into a traditional MEL measurement. So if we have a look at what's going on in here, we just have our magnet pole pieces from the electromagnet. And in the sample stage is the OLED and a resonator. And then we have our objective, which sends light up basically to our camera. So this is a schematic of what it looks like. And then we can do it for 5 times magnification, for example. So we can see that we can get a fairly decent spatial resolution here, but you can't really see too much. So then what we did was, rather than sitting at 5 times magnification, we moved up to 20 times. And when we do that, we get something that looks like this. So we can now resolve some sort of detail that seems to be there. And if we have a look at what's just happened here, we've got 2 things going on. The first thing is, this is the mean of each frame plotted as a function of magnetic field. So if you imagine that we've taken a frame like this for each field value and we sweep through a magnetic field range, as you can see here, then effectively we plot the mean, we're going to get MEL. And so now this is effectively what has been done by many others before in literature. It's just some monolithic device measurement of MEL. The difference now comes from this top part. So what this is the deviation from the mean. And so what we're seeing here is, I guess, the spatial resolution of magnetoelectroluminescence on a micron scale. So in order to get a better grasp about what's happening, we just look at the MEL. This is not the deviation anymore. This is just the pure MEL that's still spatially resolved. And so we take that at 100 Gauss, just a single frame. What we can do is we can go to every single pixel. I've just chosen 4 here, for example. And then we can plot the MEL for each pixel. We can fit that to some function. And that function is a 2-parameter fit. The first parameter is the amplitude. The second parameter is the half width. And so the amplitude tells you about the saturation of this material when it comes to MEL. That's basically how much field you need to apply to suppress spin mixing. But the half width gives you some constant which scales with the hyperfine interaction strength, AHF, which we showed before with the deuterated and hydrogenated material. So if we can now extract these parameters and plot them as a function of the spatial map, then we have spatially resolved hyperfine interaction strengths. So before I get to that, I'll just start off with the amplitude. So you extract the one parameter from this MEL fit, the amplitudes, for all points in space. And then we see some correlated structures here, which is actually quite frankly surprising. So there is some correlated structure, and you can now pull every point out and you can plot this as a histogram in order to get some measure of the variation of this guy. So you can do that there. We've done this for several current series. I'm just going to move on because I guess the amplitude is not as important as the half width. So we move over to the half width now of the MEL curve. So we can see that's the half width, that half maximum. And so we point that for every, we plot that for every point in space. And we also see correlated structure, which is very interesting. So what this is telling us is that on a micrometer scale, that the hyperfine interaction has some correlated structure. And now we can do the same thing that we just did with the amplitude, and that is we can plot the distribution of this guy, and we see that it is normally distributed, which is a good sign. And the reason why we say that's a good sign is, unlike EDMR, we're looking at spin pairs for MEL. So the effect of applying an external magnetic field should equally affect the electron and the hole within the spin pair, whereas EDMR targets each ensemble separately, or each constituent of the spin pair separately. And so to explain what I mean by that, we go back to our EDMR curve, and we see that we can pull out the electron and the whole ensemble independently of one another. Turns out that what you can do with this is you can now find the expectation value for the absolute difference in Overhauser fields experienced by the electron and the hole. So it's a bit of a mouthful, but if we think back to the picture before of we have our electron and our hole on 2 localized sites, they each have their own Overhauser fields. And effectively what we're saying is, when we look at MEL, which is a spin pair effect, we're not singling out the Overhauser field from either the electron or the hole. What we're doing is measuring the difference in Overhauser fields between the electron and hole. And so what we can do is we can pull out independent random variables from each of these normal distributions, and then we can plot these. And then that's what this equation is. And this has been experimentally verified back in 2010 with a spin beating paper. Anyhow, and so we use this technique to calculate the expectation value for the difference in Overhauser fields, which comes out to be about 7.23 Gauss. Now what we can do is we know that the B half scales with the hyperfine interaction strength. And so we can go ahead and measure that. So I've included a few extra currents, but the current that we've done all our work with so far is 70 Gauss, has a B half of 70 Gauss, and that's at 0.4 microamp per centimeter squared. And so the idea is we can use this to find the scaling factor, because we know that B half is only proportional to the hyperfine interaction strength, whereas EDMR gives you a direct measure of the distributions. So this number should give you that difference directly. So if we go ahead and apply that, we can scale back our B half distribution, which I showed in the previous slide, in order to give us a real what we think is a real distribution of the hyperfine interaction strengths. And so one measure of this variation in this parameter would be to take the full width half maximum of this distribution, which we see is about 1.6 Gauss. So the takeaway message from this is that we're able to use spatially resolved MEL in order to find the distribution of hyperfine interaction strengths, which is underlying in the material itself. And that is very, very important to know how that varies if you want to perform OLED magnetometry, for example, on miniaturized devices, right? And so this is a first step towards that. And I'll just very quickly go through a few other things. What we can do is we can just calculate things such as the cross correlation between the amplitude and the half width parameters for each point in space. The reason why I say this is fairly important is there have been several studies which try to find what this relationship is between the saturation and the half width of the MEL curve. But in order to do that, you need to fabricate multiple devices. And as you know, fabrication conditions can change very easily. And sometimes these conditions are out of your control, humidity, whatever it is. And so we've now found a method to do this on the single device with a single measurement run. You don't need to worry about decay or device to device variation. It's all right there. And what we find is actually that there is no obvious correlation between the amplitude and the width, right? So there's no correlation between the hyperfine interaction strength and the saturation value of these MELs. And the reason why that's important is we're only hitting 9% over here, but there are certain devices which can hit in excess of 4,000%. And that's really important for dealing with sensitivity if you want to make magnetic resonance sensors using OLEDs. Anyhow, so it's important to know that there's no relationship here. And the very last thing that we've done is we found a method to calculate what the characteristic correlation length is of this correlated structures. And in simple terms, what that is we look at every point on this map and we calculate the similarity between neighbors to the point at which, say, a point in the middle of this cluster shows no more similarity to a point that's outside of that cluster. And so we come up with this technique to do that. And actually it's known as Moran's eye. It's more often used in geoscience when I guess they're using satellites to map things. So we apply this to our spatial map here. And it turns out that we can see some characteristic correlation length of somewhere between about 4 to 6 microns. So this needs a little bit more work in terms of, I guess, finding a surefire way of defining the cutoff. We have to decide how do we want to find the cutoff length for this. But I mean, you can see what that looks like over here. And so that thing kind of dies down around there, around 8 microns. But yeah, the cutoff would be about 4 to 6 microns, somewhere in there for this characteristic correlation length. And so now the idea is if you can fabricate a device which is within this range, then you could get more reliable sensitivity from your sensing out of OLED magnetometers. Anyhow, so I'd just like to thank everyone involved in this project. I apologize, I've gone a few minutes over. But yeah, that's pretty much it. So yeah, thanks for your attention.
Thank you very much, Billy. Another interesting talk. So once again, I'll open up to questions from the audience.
Can I ask a question before I have to go off to another meeting? So thanks very much, Billy, for that. It's all very interesting, spin, et cetera, et cetera, et cetera. So in your analysis, how do you take into account the concentration of the spin? So, you know, if you have an unbalanced OLED, then it's not working at, you know, in terms of injected holes and electrons. How does that then affect your analysis of the effect of the magnetic field?
There are several studies which have been done on ambipolar devices versus unipolar devices. And so you do get changes. The MEL changes drastically. Sometimes if you do hole-only devices, you get a negative MEL. And so I think the reasoning behind that is you move from polaron pairs, which are opposite charge carrier pairs, spin pairs, to bipolaron pairs, which would be like charge carriers. And so that effect may be different to the polaron pair effect. And of course, you don't get recombination in those studies. You look at magnetoconductance, so it's more magnetoresistive effects. And yeah, it's a little bit more complicated, I would say.
All right, thank you very much. So I've got to go. So thanks from me to both speakers today. It's been really brilliant.
Cheers, thank you.
We have a question in the chat. So Laszlo Fraser says, when is ODMR a good choice?
So ODMR is a good choice. It depends what you want to do, right? So you could use EDMR to get a monolithic device measurement. So if you want to do magnetic resonance sensing, you could effectively just fabricate a small monolithic device, perform EDMR, and it would achieve the outcome that you're looking for. ODMR would be helpful because you can now apply spatially resolved techniques to that. So if you had, for example, a magnetic field which was not some constant field, but had some shape to it. So say you had some structure, like a resonator structure or something, and the field was a bit wacky, so it had some shape to it rather than just field lines going through, then using ODMR would allow you to detect the shape of the field. So the idea is that the OLED acts as a magnetic field sensor. With EDMR, you would lose the spatial resolution. With ODMR, you'd maintain that spatial resolution of the field that you're detecting. So I guess that would be one example of where it would be useful, particularly in sensing. Besides that, they're kind of measuring the same thing. Yeah.
Yeah, and another question was, why are the Overhauser fields different for electrons and holes?
So the main reason why Overhauser fields vary between electrons and holes, I guess I gotta go back. Yeah, so if we think about if we look at what's happening here, I've done this on purpose. So the delocalization of the electron is less than the delocalization of the hole. And so it turns out that this is true, and we know this is true from EDMR. And so depending on the size of our delocalization, we're averaging over different numbers of nuclear spins. And it turns out when you average over a larger number of nuclear spins, due to the central limit theorem, you average towards zero. And so the EDMR components, which I show over here, the broadening of these components tells you about the delocalization, or the size of these individual polaron pairs, which of course affect the strength of the Overhauser fields. And in fact, that's just a direct measure of that there. Yeah.
Very good. So there's maybe some more discussion, but I think I might kind of close the formal part of this, and we'll end it up here. So thank you very much, Billy and Daniel. Excellent talks from the both of you. So I'll stop the recording, but we can keep the session open if people want to continue these discussions.
Cheers.